So some of you may know a little bit of background behind this talk. I've been working on a little side project for probably 2.5, coming up to 3 years now. And it started as a bit of an experiment, just sort of out of curiosity. You know, working in tech leadership roles, I'm often required to complete, you know, security surveys, questionnaires and stuff. And customers will often ask, you know, I got this a lot at Expert 360 when we had to, you know, jump through the ringer with big banks and insurance companies and stuff. They would ask, is your data encrypted at rest? I'm like, yes, of course it's encrypted at rest. But it really, I started to reflect on what that actually meant. What does encryption at rest mean? And what security risks is it protecting us from? And if you think about most cases, the data that is encrypted at rest is a file system somewhere. A database may be running on that encrypted file system. And really all it's protecting you from is the loss of that hard drive. But if you think about it, a hard drive in Amazon or Azure or GCP, I mean, where even is that hard drive? And somebody knows where it is, but it's not, you know, it's probably an Amazon engineer. And if they do know where that drive is, it's going to be destroyed at some point anyway. So it's probably not the biggest risk from a security perspective. So I wanted to start exploring what other options there were. But before we do that, let me just share with you a couple of stats. For those that have seen, I have done this talk, a similar talk on this topic before, so some of you may have seen these stats. I won't go through them. I'll just go through them quickly. But last year, Q3 2019, the Office of the Australian Information Commissioner had some reports. So they had 245 reported data breaches. That's not accounting for the ones that weren't reported. 62% of those were malicious attacks. 42% contained financial details. 27% contained health information. And that's pretty alarming. And actually, the database and search indexes are still a major attack vector for hackers because it's very hard to secure them effectively. And you know, that's where all the juicy data is. One I like to share with everybody, not because it's any different to most attacks, but for the size. So this was 80 million records were exfiltrated from Anthem's medical database back in 2015. So it's 80 million is a lot of healthcare records. So databases and search indexes must be at the heart of any threat model, if that's where we're putting all this sensitive data. And data encryption can provide the necessary protection, but it comes with some challenges. So let me talk through some of these now. So obviously, you think about the default state, that's no encryption. It gives you plenty of utility. You can do anything with your data, but it doesn't give you any security, at least not in terms of the secrecy of the data. You know, you're relying on things like password strings and you know, other authentication systems and so forth, and firewalls. Transparent data encryption we've talked about. And then there's this other idea of field level encryption, which does improve security quite a bit in some cases, not in all. But the trade-off is that you lose a lot of utility. You can't really do a lot with that data once it's been encrypted. So the question is, can we have both? Can we have security that is also useful? Can we apply security to our data and still be able to query it? This is just a summary of what I've just talked about. Transparent data encryption, that's just a diagram of sort of explaining the issues. You know, once the data is encrypted on the file system, the key to decrypt that data and encrypt that data has to be on the same physical machine or virtual machine. And so once the data is all loaded into memory, it's effectively fully accessible. So it's not protecting you from 90% of attacks. And yet this is the question that most you know, security surveys or assessments are asking: is it encrypted at rest? So we've sort of talked about that. One of the examples in Elixirland that does this idea of field level encryption is called Cloak. So this doesn't do transparent data encryption. It's actually encrypting each of the fields, say in a Postgres or a MySQL database. And so in this example, you can see an ecto schema where there's some encrypted field, which is using a sort of standard encryption scheme like AES. What it would look like sort of under the hood is effectively this is encrypting the data in your application before it gets sent to the database. And so you might have, you know, name, email, and age in your database, and all of these fields are secret; they're hidden away. But that comes with some challenges. One, the database structure is still visible, and we'll talk a little bit more about why that's important in a moment. Some schemes, so Microsoft SQL Server has a scheme in their product called Always Encrypted, which I guess is they're trying to get away from that language of transparent data encryption. It's sort of still transparent, but it's actually encrypting at the field level rather than at file system level. That uses a type of encryption called deterministic encryption, which opens up a whole kind of range of attacks, and I'll show an example of how that works. And for the most part, these schemes are not searchable. In the case of deterministic encryption, they are you can do simple key lookups at the expense of reduced security, but certainly nothing complex like ranges or fuzzy string matches or things like that. So I wanted to actually give you an example, a demo of Cloak. So Cloak is actually a great library, and it's good for some use cases, but it's got some pretty major challenges. So I'll bring up an example that I put together. So zoom in a little bit. Hopefully everyone can see that. Can everyone see my console now, by the way? Just make sure. Feel free to yell out.
Yep.
Cool. So I've just created a little Ecto model, just called it person, and pretty much just lifted it from the hex docs for Cloak. And so this has got a person schema, people table, and it's got 3 attributes. It's got email, and it's got this thing called email hash, which the author of Cloak actually recommends. And this is no, certainly don't mean any disrespect to the author, but this approach does come with some pretty major security challenges. So let me sort of demonstrate what that looks like. So I'll have a console already. No, I'll start a console. And I'm going to look in the database as well. I'll just open a tab. Sorry, drowning in tabs here. Click demo dev. So if I get all the data from the people table, you can see that it's all unreadable. So it's encrypted. Unless you know kind of what you're doing, you know, any encryption scheme looks like the next. And so if you can't read it as a human, then you'd be forgiven for thinking that it's nice and secure. So sorry, I've lost drowning in tabs. Here you go. So if I want to insert a person into the record, into the database, sorry, I can, I think I created one earlier. Click demo, create person. There you go. Say their email is, I don't know, foo@bar.com, and their age is 50, something like that. Cool. So then what I can do, I can actually do a lookup. So that's what the email hash is for. So if I, actually what I'll do is I'll show you what the email table looks, or the email column looks like. So if I get email from people, so you notice the last one looks like that. If I do that same email address again, insert it again, you should see that it's a different string. So that's because it's using non-deterministic encryption, which is great. However, I can't do any lookups. I don't know, there's no way that I can do a string comparison or anything like that in order to look up the email address. So what this example uses is the email hash column. So I'll just search from that. And you'll notice that for that value, it's the same for in each case. So that's how I can look up a value. So if I want to retrieve a value, so I can go demo. I think I created an example of this. Get person email foo@bar.com, and oh, it wants me to. There's no uniqueness, so I can't guarantee uniqueness, but you get the idea. Actually, I think I created one earlier. Maybe that one. Yeah, cool. So I can look it up based on that. I'll come back to the email hashing problem in a moment, but there is one other challenge that I wanted to share. So I'm also storing age. And so let's say I wanted to search for everybody that was, say, over a certain age. And I created a little function in here just for demonstration purposes. So I've got a function called people. It's going to go from person where age more than X, and then retrieve all those records, which is a perfectly reasonable use case for this kind of application. Let's assume it's a medical database or something like that. What did I call it? People and older than, say, 25. And babao, I can't do that because I can't convert. There's no comparison. There's no reasonable comparison operator between the integer 25 and the encrypted binary in the database. So I've suddenly lost a huge amount of utility. Also, if I don't know the entire email address, so I wanted to search on that, that doesn't help me either because it needs to be exactly what I'm searching for. That's the only way I can look it up. So there's some pretty major hits to utility. But I also argue that there's some pretty major hits to security with this method as well. So let's take an example of a medicines database that's storing users, say, along with their email hash using the mechanism we talked about a moment ago, and a hash of their medication. So let's say, if you think about that in plain text terms, if you have an email address in one column and then all the names of all the medications that that person is taking in another column. Obviously, you'd use, you'd normalize that data a bit in practice, but just for argument's sake. So there's actually a few things I know about this just by looking at it. So firstly, because the hashing scheme is deterministic, I can see that this is the same person. So now I know that this person is taking 2 medications. Right, okay, so that's interesting. That's already leaking some information. The second thing is because the hashing scheme that it's using it's not keyed, it's not using a salt. I can, and it's deterministic, obviously. I could say, take the hashes of all of the common medications and compare those hashes to the hashes that I generate. Can do it even faster using something called a rainbow table. And I can actually, through a brute force mechanism, determine which medications this particular user is using. Then I could even apply the same technique to their email address. Just take common email addresses, craft it. SHA is really, really fast, so I can do billions of hashes in a very short amount of time, and I can get a whole bunch of information. So this is the hash of Valium, and this is the hash of carbamazepine, which is an anti-epileptic drug. I'm not taking those medications, just for the record, but that would be pretty revealing information if somebody was able to get access to this database. So a motivated attacker is not really going to be stopped by this approach. And actually, from a paper back in 2015, due to Naveed et al., showed that if these kinds of deterministic encryption schemes, the particular ones they were looking at were called order preserving schemes, showed that they could actually reveal up to 90% of the data with some pretty simple tools. And one of the reasons they were able to do that is because they knew what kind of data it was. So that comes back to why the structure is really important, or hiding the structure. So it's really interesting. So essentially, even though we're encrypting email address using a secure scheme like AES, which is provably secure and is still considered the best practice for encrypting data, because of this hashing scheme that we've added in order to provide a bit of utility to this system, we've dramatically weakened the security profile of the database. And so I always love showing this diagram. You're only as good as the weakest link. So you can put up this giant gate, but if you've got a little hole on the side, then the gate is useless. So there was a scheme developed by a couple of Stanford PhD students back in 2016. And they wrote a paper on it called not order preserving encryption, but order revealing encryption. I've got another talk on this topic, goes into a bit more depth on my YouTube channel if anyone wants to take a look. But essentially, the order revealing encryption scheme, instead of giving you a single ciphertext, it breaks the ciphertext down into 2 parts. And so what you can do is when you're storing the data, you first encrypt the plain text into the left and right ciphertext, but you only need to store the right ciphertext. And so then when you're storing the right ciphertexts, they behave very much like the AES encryption we talked about before, which is provably secure and non-deterministic. So you don't have these issues that we described. And then the left ciphertext is actually used to perform queries. So I can generate a left ciphertext and use that only at query time. There's a small window where the security model is slightly reduced, but it's no further reduced than a deterministic encryption model, and it's only for a very small period of time when you're executing that query. The live running database is not susceptible to these issues. So as I mentioned before, we want to hide structure. So hiding structure is critical to avoiding these kinds of inference attacks. And it was a key design goal when I started creating CipherStash. So these slides are a bit out of order, but essentially this shows an example of what can sometimes happen in these kinds of models. And actually, it's sort of what, in a sense, it's what the Cloak example has done as well. So let's say a company cares about security, so they turn field level encryption on, maybe using something like Cloak. And then they go, oh crap, now I can't actually search my data. So they move all their data into a weaker security system, a reduced security model data storage mechanism. In the Cloak example, it was using SHA hashes. Lots of people use Elasticsearch. Elasticsearch is great, but it's terrible for security. And so then they realize, well, shit, now our model is only as good as its weakest link. And so the field level encryption is essentially useless. So this is where CipherStash comes into play. So I wanted to share sort of the background as to why I wanted to get on this path. What CipherStash does a little bit differently is, unlike Elasticsearch or Solr or Lucene, which does all of the text analysis server side, you know, you think about Elasticsearch, you take a document, you send it to the server, it does a whole bunch of tokenization, token filtering, stemming, language analysis, all that kind of stuff, and then stores it in its inverted index. What CipherStash does is it does most of that work client side. So I've got a record, perform term and text analysis in the client, and the client could be, you know, a Elixir Phoenix app, a Rails app, even a JavaScript app running in the browser could do this. That analysis pops out some terms, and then those terms are encrypted under the order revealing encryption scheme I mentioned before, and that's sent to the CipherStash API, which is a gRPC API, which I'll get to in a moment. So effectively, CipherStash never sees either the encryption key or the data itself. Never sees any plain text. It only ever sees those encrypted terms. Then similarly, to run a query, I run the same sort of process, but now instead of doing the analysis on a document, I'm doing the analysis on the query itself. So let's say I wanted to do this search, Dan and citrazine. Citrazine is just an antihistamine. And I'm going to do the same term text analysis on it. I'm going to encrypt using the order revealing encryption scheme. I'm going to send just the left ciphertext to the server to do the query. Once again, CipherStash doesn't see any plain text data, has no idea what that query is, but it knows how to compare the query to the data that it has in its database. And then it sends back an encrypted result, and then that's decrypted, and then finally the client gets to see the data. So essentially, your threat model has moved the database, that's pretty cool, database out of the equation. And in particular, your free text search system out of the equation. So there's two main models that you could use CipherStash for. One of them is as a primary searchable data store, say for microservices. So, you know, this is sort of like think of it as a hybrid between something like Mongo and Elasticsearch. It's sort of a key value store, but with free text search on top. Or you could use it to augment an existing database where, you know, you've got a Postgres database, maybe you're using Cloak, and then you don't use that hashing scheme that I've talked about. You just use the more secure non-deterministic encryption, and then you use CipherStash to stick that on the side to allow you to do more advanced searches. So essentially, it gives you the opportunity to increase the level of security in your database while maintaining a level of utility. So it's just sort of a diagram that explains that. Rails, Django, Phoenix, whatever could be the application. I should only be talking about Phoenix in this talk. So to run you through what that would look like in augmented mode, I call that. So let's say that you perform a CipherStash search. Let's say that you search for the name Dan. That would return an array or a list of encrypted IDs. Those IDs are decrypted inside the application, and then those IDs are used to retrieve your records from your existing database. So just using a simple lookup like that. And then those fields using something like Cloak could be decrypted, and then those decrypted records are sent back to the client. So actually, this kind of model is very similar to how a lot of people use Elasticsearch now anyway. And it lends itself to something like GraphQL. You know, when you've got a resolver that's, say, if you're using Relay, you want to resolve your edges using the encrypted IDs, and then your nodes using the database. If you're familiar with GraphQL, that may make sense to you. A few things about CipherStash itself. It's written in Elixir, so the server is written in Elixir, and there's a bunch of reasons why I decided to do that. It's distributed, so Elixir is a great language. I'm just using the Beam and the OTP. Is extremely well suited to doing distributed and highly concurrent fault-tolerant systems. And I also wanted to make it hot reloading. One of the things that we often don't think about when we're doing deploys is how do we deploy a database? We've been spoiled by services like Amazon RDS, where you don't even have to think about deploying a database. It's just all magically works for you. So we can think about 12-factor apps and killing an application service. It's ephemeral, it doesn't have any state. But a database absolutely has state and is not typically ephemeral. So you kind of want to keep that running for long periods of time. And so using hot reloading in Elixir, maybe someone should do a talk on hot reloading if no one has done that yet, but that's a really powerful tool. So Elixir was a really good sort of fit for CipherStash. The other key design decision that I made was to use gRPC. So that's effectively G was I think originally stood for Google. It was their binary protocol for remote procedure calls. So it's just an API protocol that runs over HTTP2 instead of using JSON. So Elasticsearch and just about every other web-driven API system on the planet these days uses JSON. JSON's great because it means you can craft your API request using plain text. You can read it. It makes sense. But none of the requests that CipherStash does are readable anyway. They're all just big long binary strings that are not human readable. So it didn't really make sense to use JSON. It was just unnecessary overhead for no real gain. So I decided to go down the gRPC path. And one of the cool things about gRPC is that it supports HTTP2, which for anyone who's familiar with HTTP2, you've got this idea of server push. So client can make a request to the server can send back a response and then send more responses later on, which means you can do some cool stuff with paging data and prefetching results and that kind of stuff. So you get some pretty major speed ups doing that kind of thing. And it's generally pretty good support for gRPC. There is some good libraries in Elixir, although still fairly early. And I'm also developing a CLI tool, which I may use Elixir for, but I might also just use Rust. We'll see. The idea with the client is that I want to build lots of different clients, and that doesn't necessarily make sense to build an end-to-end client in all languages. So the thinking is that at the moment, the prototype's just in Elixir, but the long term, everything would be written in Rust at the bottom of the stack, if you like. And then I would wrap that with language-specific wrappers. The cool thing about Rust is you can run it in WebAssembly. So the same sort of free text search analysis can be done in the browser in Rust using WebAssembly, which is pretty awesome. CipherStash supports some data types. It's certainly not as fully fledged as some of the other search systems around there, but I'm working hard to expand on those and using some of the libraries from Rust. There's actually a Lucene implementation in Rust now, so I'm borrowing heavily from that. Supports keywords, so you can do exact strings. Supports integers, unsigned integers of 56 bits. That's not a typo. It's not supposed to be 64. It is actually 56 bits. I'll explain that in a moment. A special type that I've developed called orderable strings, and of course free text. And then I've got a few things coming. Particularly of note is GeoPoints for doing locality search. You can show me all records within 50 kilometers of a certain point, for example. So the reason that unsigned integer is 56 bits and not 64 is because of this idea I've had to develop to support Cypherstash that I'm calling data packing. So the order revealing encryption scheme can work on effectively any size, but the size of the ciphertext grows exponentially, or at least quadratically, with the size of the plaintext. So I didn't want to use any more than 64 bits, otherwise it just ended up taking up way too much data. So I had to try and find a way that I can pack as much data as I could into 64 bits. So the way that I've done that is embedded a field. So the field could be, you know, an ID, an integer representation of name, email address, age, whatever, and then leaving the remaining 56 bits for the data. So I think 56 bits is sufficient for most applications when you're talking about numbers. 64 is a lot of numbers. This also has the added benefit of hiding the structure. So because the whole integer is encrypted, then you have no idea what the field is. You can't tell the difference between field and the data. So there's no structure revealed. That gives us up to 256 fields per collection. To do strings, I'm using ziphash, which is like HMAC or SHA, but it's a bit faster and takes up less space. By truncating it down to 56 bits, I do lose some. There's the small risk of collisions, and to tackle that, I'm doing some client-side filtering. So if you get a couple of results back that have collided, then you can filter those out. Skipping over this pretty fast because there's a lot of depth here. For longer terms, I've experimented with splitting terms across two different fields. So if you've got long data types, you could actually have field one is like part one of that value, and then field two is part two of that value. So that works quite well as well. One thing I wanted to touch on very quickly is paging. So I take quite a different approach with paging in Cypherstash. So most people would be familiar with the idea of if you do an SQL query or any kind of pagination query, like with Elasticsearch, you would normally go with a limit and offset. So give me 20 records and then offset it to the 40th record or whatever, and then 60th record and then 80th record or whatever. Cypherstash uses a different approach. It still uses limit, but instead of using offset, it uses after. So that's saying, give me the next 10 records after this term. Now, there's a very particular reason why I've done that. It's similar to GraphQL, but it's not for the same reasons as GraphQL. The reason is because traditional pagination leaks information. So let's imagine you've got Cypherstash sitting here, and this person, let's call her Alice, is making a query. She sends this encrypted query, and she says, give me the first 10 records, but give me a start from the 20th record. So this is if I was doing limit and offset. If there was an eavesdropper who was able to see all the queries being made on the Cypherstash server, Eve suddenly now knows something about the data. Eve knows that there are at least 20 records of that particular data type. You see enough records, and you can start to build up a bit of a picture of the statistical spread of the information. You can start to identify what, maybe if there's lots and lots of one particular type of record, then that's very likely to be a particular, value that you might be looking for. And so it might not leak a lot of information, but I wanted to try and avoid any kind of leaking of information whatsoever. So compare this to the limit and after mechanism that I've talked about. You would never know whether this was the first record or if this was after, or the 1000th record. So it doesn't leak any information to the server. Quick note on performance. So this is the order revealing encryption scheme. Just wanted to show you what this looks like in terms of running some very simple queries. So if you run this is with 10,000 records in the index or the collection. If you fetch one record just using a simple equality, then it's about 50% slower, all the way up to the worst two cases, which are the last 100 records, about 2.5 times as slow. So that's actually pretty reasonable, and you can. It's the kind of performance that you can easily make up for with very fast hardware, lots of memory, fast SSDs, and high CPU configurations. So that's pretty reasonable. That's sort of what the ORE encryption scheme looks like. You can compare the block size. So I'm using a block size of a plain text size of 64 and a block size of 8. So that shows that your ciphertext size, that's both the left and the right, is 464 bytes as compared to 8 bytes, which was what a 64-bit integer would take up. So you can see it takes up a lot more storage without much impact on speed. So the biggest issue with CipherStash is the amount of disk it uses. But having said that, disk is cheap. In my tests, I haven't really run into any storage limit issues so far. Right, let's have a look at a demo. So I'll bring up my screen. Any questions before I jump into the demo, by the way? Or do you want to hold them to the end? I'll push on. So let me start with the innards of CipherStash. So at the moment, the back end of CipherStash is actually Postgres. That's not going to stay that way. I'm actually going to move it to a database called Lightning Memory Database using a lower level storage engine. The reason I'm using Postgres now is because it's nice and easy, but I'm basically only using it for its B-tree indexes. I'm not really using it for any of its other features. And actually, Postgres is not super well suited to this kind of application. But I'll show you some interesting stuff. So firstly, I want to show you that I've got a documents table. So I'll just grab one of those. You can see that this is all encrypted. So a bit hard to read on this size. Have a look at the documents table. So it's got only a value and a collection ID and an ID. And so that's essentially like if you think about the parallel and Elasticsearch, it's like the source of the document. So I can actually use this as a simple key value style document store as well. And that's just encrypted under AES. So that's pretty secure. And then I've also got this table called postings. And this is where literally all of the index information sits. And I'll show you the data there. And you can see that there's no structural information leaked there whatsoever. I don't know whether these are strings or integers or geopoints or whatever. It's all just sort of plunged into the same blob of unreadable data. In this database, I've got I think just about 100,000 records, 100,001 records. So that gives you a bit of an idea of how fast this is, or how well this is performing, given that amount of data. So let's jump over to Dr. Elixir. I've created what's going on with my terminal? I've created a sample application, which is just an Elixir Phoenix application. And I've created a schema struct called patient. And I'll start down here. This is a pretty standard schema bar for a couple of exceptions. So you can think of this as, the equivalent in normal SQL land is a patient's table with name, email, date of birth, and height. And in fact, there's no reason why you can't also keep this information in a traditional database using something like Cloak to encrypt that safely. But then I've also added, by using the CipherStash analysis module, have added some search indexing capability using CipherStash. So there's 3 fields that I've decided to index: name and email. I'm using the type ahead analyzer type, and that's essentially, I can show you what that looks like in a moment, but allows me to do like auto-completes. And then height using that UNT56 type that I mentioned before. It doesn't actually need to be 56, so I could probably shorten it, but given every ciphertext every plain text needs to be 64 bits anyway, I might as well use it. And that's also, once again, to hide information. So every ciphertext is the same length. And then I've also just mapped this. You wouldn't obviously keep this in the code like this, but just for demonstration purposes, I've mapped which collection ID. So you can think of this as the equivalent of the table name, near enough to that sort of concept in traditional SQL databases. And so then I can show you what a query looks like. So there's a few different things I can do, but let's start with something simple. I think I'll start with that, and then I'm going to say, so create a little service, just a bound of context essentially, patients search. I'm going to search by name. So let's go Dan, and that's giving me a whole bunch of data. It's very large on that screen. So that came back really, really fast, and that search by name. This is all just from Faker, so that the names and email addresses don't match, and there's some really weird names in there. But you notice that it's not matching on the exact name. It's doing a fuzzy match. So it's looking for, it's actually doing what's called an edge n-gram analysis. And so I can now do, well, okay, so I'm looking for someone called Dan, oh, there's Kayla Daniel. Let's see if I can find her. Okay, cool. So that managed to narrow it down. So it doesn't even matter what order it in. So if you're familiar with search systems, this is doing like a bag of words type match approach. I can also do something a bit more low level. So let's go Ecto query, and I'm going to go from patient. I can do a range query. So let's say I want to find all people who are taller than 2 meters. So height more than 200, that gives me a query. And I'll go, I think I aliased this earlier. No. And that's giving me all users that are more than 200. So I've done a range query. Even though that's all encrypted, I can do the range query quite easily. And then I can chain things together. So we'll go. Now, I haven't actually written a macro to change operator in Ecto. So I'm just using the equals operator to match on a fuzzy match. It's absolutely not equals. It's more like, but I didn't bother changing that. So this one's obviously not going to match any records. Oh, sorry, that's all 200 people where there's name like Dan. So yeah, 200. Height more than 200 and name like Dan. So there you go. And then I've also, just to sort of show you how performant it is, I created a little front end for it. So it's a bit of an excuse to use live view. So I can do sort of the same thing in here. Oops, not Mike. Mike. Something like that. So that you can see that's pretty snappy, and it's also doing highlighting. It's actually doing the highlighting client side, which is kind of cool. A couple of other things I can show you. I can do a simple get of a record. So I've got an ID here. So at the moment, CipherStash just automatically stores the entire record, but you could probably configure it so that it only stores the index. So let's take that ID and go patients, get patient. So that retrieves it and just serializes the struct. And the reverse is also true. So I can basically do all of the Ecto operations. To show you a little bit of code as well. People are interested in having a look. So I've started creating this CipherStash Ecto extension. At the moment, it's all just bundled into one library, and I'm a bit embarrassed to show this code because it's still a mess. But I've started to build an Ecto adapter. I'll just sort of get to the meaty bits. So this is doing insert. So you can basically just take the Ecto adapter behavior and do all the things you need to do. So as you can see, that's doing the analyzer perform or analysis there, and then calling the lower level CipherStash API. And then queries are a bit more complicated. Where's an example of a query? I had to learn how to parse Ecto queries. So I had to do all this rubbish. Where is it? Parse query. So it gets all really messy and complicated and what have you. But anyway, you get this sort of idea. I'd be happy to go through that in more detail if there's interest, but I'm conscious of time. And then just to sort of wrap up, what's coming. So one of the really cool things about Elasticsearch is its ability to do facets or aggregates. So if you do a search, I might want to see what's the average age of all the people who were returned in that search. So I've got a way I can do that with CipherStash. That's coming. proper ranking schemes. So the standard ranking scheme in Elastic is it's called a Okapi BM25. That's going to be pretty challenging because it uses floats. But what I'm looking to do is a sort of an integer approximation of a Okapi BM25. We'll see how that goes. As I said, moving to LMDB. I need to be able to do key rotation and reindexing, more analyzers. And the most interesting one, I think, in this list is distribution replication. And so one last thing I wanted to share with you before I wrap up is what kinds of opportunities we now have when we change the paradigm, I guess. I don't like that word, but this is really a change in paradigm. So if you think about traditional database management, you'd have primaries and replicas, and we care a great deal about logical separation. It's often one of the things that you get asked on a security questionnaire. Is my data going to be logically separated, like a separate database or even a separate virtual machine from everybody else's? And then that means that in order for you to support that as a DevOps person or as a vendor, you've got all this extra overhead to create the different primaries and replicas. So there's lots of logical separation over here. In CipherStash, you don't actually need to worry about that anymore. You can chuck all of your customer data in the same place. And that's because your encryption keys now effectively provide the logical separation. So you don't need to do all this ceremony and song and dance to create new databases or new virtual machines. You can put it all in the same place. So even though the data is a lot bigger and takes up more space, you're actually starting to get these really interesting economies of scale. And that's where I'm really excited about, distributed Elixir and so forth, because all of your data can cohabitate, but only the owners of the keys can query or get access to the relevant data. So that could mean some interesting new scaling opportunities. So that's really it. Wanted to call out that even though it's still only at the proof of concept stage, I'm hoping to make this a business at some point. So I'm looking for people to do a POC. If anyone's interested in having a play with it or just chewing the fat, I'd love to talk to you about it. Tried really hard not to make this a sales pitch, but sorry if it came across that way. If you want to get in touch, there's my email address down at coderdan.co, my Twitter, as Paul mentioned earlier, and I've got a couple of GitHub links there, but the client libs haven't been open sourced yet. They will be soon. I'm planning on tidying up a bit, but also getting some licensing. Got to find the right license. I'm just getting a lawyer to give me some advice there. As soon as that's done, we'll open source them, and hopefully people can have a play and contribute. So that's it from me.